Hey everybody, Kim here again with another video in the controls engineering in the context of Disney and attraction engineering in general. And another hardware video for you. This one is a bit of hardware specifics, right? I kind of touched on the fundamentals last time. We talked about sort of the dichotomies that appear in hardware in terms of low voltage, high voltage, AC, DC, analog, digital. Wanted to just kind of touch on a few more sort of specifics to controls hardware for you here. Something that's more of a standard practice convenience thing. If you look over here, you can see in this picture, this labeled one here is your processor. This is an Allen Bradley processor. This big left guy here with the one on it, that is the power supply for this whole rack of stuff. This card, first card here, is an Ethernet card from the looks of things, and then further down is your I/O modules. So that would be kind of these guys. They're local I/O. They're local to that bank, right? Since there isn't a processor on this row of cards here, this would be a field cabinet. You would see this installed somewhere else in the plant because it doesn't have um, what would be in this picture. This is also an Allen Bradley processor. You can see this is the big power supply on the left there. These five cards with the red and the green kind of labels on them, those are I/O, local I/O. And this guy with the key here is an Allen Bradley processor module. It's the equivalent of this. The way it gets to be so much smaller is that they offload some of the work to the modules next to it, and the you can barely see it in the back here. There's a big circuit board that these guys hook into in the back there that does some of the work too. So that's how they get away with it. These modules are a lot bigger than these individual slices are, and that's kind of the trade-off is you get bigger equivalents of this for a smaller equivalent of this guy. Um, but so this is local IO in this picture, and this is field IO because there's no processor there. There's just an Ethernet card, um, like what's on the end of this guy here, to connect it back to wherever its processor lives. But a thing that's interesting on here is this key is very important for Allen Bradley processors because it is a mode key. What you can do is set it to, you put the key in, you turn it to program, and it allows you to connect to that processor and upload or download software from it so you could interact with it and make changes and make it do what you want it to do. And if you switch that key to run and take the key out, it's impossible to push or pull software from that processor. So nobody can tamper with it um, without having one of those keys, which your average Joe Schmo person walking through an industrial facility doesn't have one of those keys. So they can't mess with it. And even if they had a key, they would also have to have a computer with the software that you need to connect to an Allen Bradley processor on that computer, and they would have to have the connecting cable to connect into it. They would have to have access information to know how to connect to that. There's a lot of extra safety in there, but that physical key is a really nice feature that at the end of the day, if somebody does get in with, like, if somebody hacks your industrial network or whatever and they find this processor on the network, no matter what they try, they can't do anything unless they physically go to that cabinet, physically put in that key, and physically turn it to either remote or program to connect to it and mess with it. So if they're hacking in from, God knows where, it's impossible for them to do that. It's a super good physical in-person safety feature that's just a nice to have. Which, speaking of safety features, it was something that I loosely touched on um, in terms of having things like your field IO having that heartbeat connection back to the processor. So if that heartbeat ever stops, the system goes into safe mode because I've lost communication with something in the field that's really important. Stop what you're doing until we figure out what the hell happened. So the heartbeat is a safety feature. Another really big safety feature, specifically for hardware, is what's called fail to safe, which is situations where your inputs are and your outputs are explicitly dependent on energy being applied. So an e-stop button, right? We've all seen them, especially in movies and things like that, where they slam the emergency button down and everything, alarms go off and all that kind of stuff. Those are specifically designed to wire into whatever I/O card that they're attached to in such a way that it treats things as normal while it has power. So we'll dig into it more deeply in the software side of things. It's a distinction called normally open or normally closed. It's saying, is this norm? Is this something that should be allowing power to go through it while it's getting energy, or should it allow power to go through it while it's not getting energy? Is normally open versus normally closed. Um, but the idea with fail to safe is, or like an e-stop button is the most blatant example, is that you wire steady 24-volt power through the switch. So while the button is pulled up, right before you hit it, um, energy is going through that button back to this guy. So it gets a signal in constantly that says that button has not been pushed. Everything's fine. And it will do whatever it's programmed to do as long as that button's not pushed. And the idea there is that if you hit the button, power gets cut at the switch. Power stops flowing into here. The system says, hey, I lost that signal. Stop, 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 stop. Everything goes to safe. And the point behind that is that if there's a power outage, it fails to safe. If the power in the building, in a part of the building, if the power to this bank of IO goes dead, or the power to whatever control panel the operator is supposed to be interacting with goes dead, you don't want to ignore that and just carry on doing what you're doing, because now the operator has no way to tell you if there is an actual problem, right? Like if I'm standing in front of a panel with an e-stop button on it and that panel goes dead, just all the lights go out, all the toggles and switches stop working, it goes dead. If there is an emergency and I hit that e-stop, it's not going to do anything because the e-stop, like if it was if in a reverse situation, you'd hit that button and nothing would happen because you can't get power through it because the power went out. That's why you design it to fail to safe, where the only time it works is while power is present. And if the power goes out or you hit the e-stop button and cut the power at the switch, the system says, "Hey, there's a problem. Stop." So that's a fundamental safety PLC safety engineering concept, is fail to safe. It's anything that you are worried about creating a hazard is designed to only function when you have specific signals on and coming into you, so that in the event of an equipment failure or a power failure or anything like that that's not system wide, it turns everything to the safest state that it is capable of doing. So it would trigger brake runs to stop vehicles in specific places. It would turn off fog effects so it's not blowing fog into guests' faces while they're sitting still. It will turn off animatronics so they don't swing and hit a maintenance person that's trying to deal with your power outage. All of those kinds of things are designed to fail to safe. It's something that's very much drilled into controls engineers, is anything that's safety critical is always designed to fail to safe. It's something that's very important, something that we drive into people. If there's one concept that you could ever take away from these videos, out of everything that I'm going to try to teach you on hardware and software side of things, as much emphasis as a discipline, and especially as far as Disney engineering is concerned, safety is absolutely everything. It's the top key for a reason. It's everything that we do is safety dependent. So, learning the concept of fail to safe and applying that to other situations in your life would be the biggest takeaway I could possibly give you. Is anytime you're making decisions, is the if this goes horribly wrong, do I wind up in a safe outcome? Is sort of the like generalized version of fail to safe. It's like if completely poops the bed, am I in a safe situation or am I in a bad situation? And trying to make your decision making facilitate a fail to safe mentality. That um, maybe that's a horrible idea. I feel like it's a smart way to go about things, but that's just me. I'm a very paranoid by nature person. Um, so one other bit of hardware specifics was a question that Ben asked over on Twitter, which was, how do you check that the machinery actually is doing what you tell it to within tolerances? For example, would you know if some of the pesticide sprayers in the bug theater were getting clogged up and which ones? Can you use accelerometers to watch for rough turns on Midway Mania? So, the short answer to that is no. Um, realistically, it's a kind of sort of trending towards yes kind of a question, because equipment is getting smarter all the time. The hardware that we're installing is constantly evolving to give us more feedback on what we're doing. Um, the sort of the older an attraction is, or the older a manufacturing facility is, the less visibility we have on that kind of stuff. We do the best that we can, right? You have pressure sensors, temperature sensors, flow sensors, viscosity sensors, temperatures. Like, I mean, any value that we can realistically get a sensor in there to measure, we're trying our best to measure it when it's important to either the function of the system or the safety of the system. We want to have visibility on what's going on there. So, as equipment continues to evolve more and more and more, we're installing additional types of sensors, new kinds of sensors, and more of them in order to give us that feedback that we need to make smarter decisions on the equipment that we're working with. So, the vast majority of attractions depend on manual human inspection. We have maintenance teams that go through and do routine inspections and routine maintenance. The cast members that actually operate the attractions do walkthroughs at the start of the day to check for issues. Anything that's not running, not working, not looking right, anything that's out of whack, they're looking for those things at the top of the day to note them, to pass to maintenance for maintenance to follow up on. So the vast majority of what we do depends heavily on them doing that for us to find what those problems, so that way they can get fixed by maintenance or escalated to us if it's a big enough. I keep saying us and we, but um, if it's a big enough issue for the team to handle higher up the ladder. So, but in newer attractions, newer devices, the brand new generation of animatronics, for example, things of that sort, um, we're getting substantially more information back out of the system. Instead of just telling it what to do and hoping it does what it's supposed to, it'll tell us, hey, you said to move 10 degrees, I moved 9.9 degrees. We'll get that level of information back out of them. Some systems we care about that more than others and put more effort into that feedback loop than others. But if it's something that we really care about, there is a massive amount of information coming back out of those systems so we can know. So the specific examples that you mentioned, the bug theater pesticide sprayers, that would be something that's dependent on manual inspection. We would have level sensors in the tanks that the liquid is kept in to know when they're running low so somebody can go and refill them, that kind of stuff. But if a sprayer is clogged or something, that would be something that you'd catch on a maintenance inspection, routine maintenance inspection. And likewise, accelerometers in Midway Mini, I'm not sure if they actually have them in there. You could do that. There are examples in industrial settings, manufacturing facilities, things of that sort, where they're starting to incorporate um, vibration sensors. So what they're looking for with that is the kind of thing where over time wear and tear on parts, they're not as tightly fit as they were when they first got put in, so they start to wobble, and that wobble creates vibration in the equipment. So having vibration sensors on your equipment can alert the system, hey, something in here isn't up to spec anymore. You may want to get a maintenance team out here to take a look at it because the machine's got some wobble to it. Um, which that carries into the last part of this little video here, which is predictive maintenance. It's an up and coming thing that industry is starting to do more and more of. It's thanks to the intelligent hardware that we're smart hardware that we're installing that's able to give us all of this information back, combined with the ability to process all of it, right? We have AI, machine learning, big data that can chew through all of this steady stream of data that we collect off of all of the equipment, and it can start to learn to guess when things are going to break before they actually do. So traditionally, you would do preventative maintenance on equipment. You would say, hey, this light bulb is rated for 1200 hours. So we'll monitor how long it runs and pop an alert at 1,000 hours that says, hey, it's been 1,000 hours. We don't want to risk the bulb blowing out. Go change it. Um, and that's preventative maintenance. So what predictive maintenance is trying to do is measure when the bulbs actually blow out, right? If you note, 1100 hours, 1175, 1200, 1250, 1300, that over and over and over again, when they actually do go bad, you can start, if over a large enough sample of data, right? If you're using 10,000 of these light bulbs across your entire company and you keep track of, how close to 1200 hours they blow out either side of it, eventually it learns that 80% of the time the bulb doesn't blow out until 1275 hours, instead of every bulb always being changed at 1100. You push it out, now you're only replacing them at 1250, so you're getting extra life out of every bulb. Out of 80% of all your bulbs, you're getting extra life. Out of that 20%, they'll blow out and you'll have to go change them. But that cuts down on your maintenance costs because you're not changing them out for no reason. You're only changing them out when you have to. And it cuts down on your parts cost because you're not replacing bulbs as frequently. You're getting an extra 150 hours out of 80% of your bulbs. You multiply that out by 10,000. The savings grow exponentially. The numbers boggle my mind sometimes when you get onto industrial scale of budgets and part costs and things like that. The numbers just shake your brain because you're like, I'm sorry, how that you spent $100,000 on light bulbs last month? What? The numbers just don't make sense to a normal person because your normal person budget is nowhere near that scale. It just kind of shakes your brain. Um, so to answer your question, there have been no, but we're moving in that direction is essentially like every generation of technology is getting of hardware is getting smarter and smarter, and it's giving our software systems more and more information to work with. And the more information we have to work with, the easier it is for us to do those kinds of things that you're asking about. Like if we have a sprayer that has a clog sensor or at least a moisture detector at the tip so it knows if no liquid came out the last time you triggered it, that could alert us, hey, sprayers 3, 5, and 7 didn't have any liquid come out last time. Maybe you should go look at that. That's something that the hardware is evolving to allow us to do. um, Part of it is a question of necessity. If a maintenance team on the night shift walking by and triggering a show one time can do that too, does it make sense to spend $300 on a sprayer instead of $50 on a sprayer? That those kinds of decisions get made all the time by people. Um, but the technological side of things is trending to allow us to do those kinds of things in a much more substantive way on a massive variety of devices and hardware and equipment as we sort of evolve both in this industry and all other industries. They're all pushing in this predictive maintenance direction, and it's really interesting stuff. Trying to see how the machine learning algorithms chew through this once you establish that data collection and start collecting massive volumes of running data and see them go start to do okay, well, you saw it break here, 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 and here, so if you notice this or this, that machine needs maintenance right now. That kind of stuff is really cool. It's not my specialty in the field. I don't really mess with the machine learning algorithms and the big data side of things, but I've worked a bit with some of the smart hardware collection half of that equation, and it's really cool stuff. It's you can AI and machine learning is its own distinct field that you could spend ages going through YouTube videos and things learning just about AI and machine learning algorithms and the kind of things that they're capable of doing. So it's a really deep field to dive into and fascinating stuff. What it's evolving all the time. I know I'm going to get the "Oh my God, Kim's going to build the Skynet. It's going to kill us all" comments from particular people, but AI and machine learning is fascinating stuff. I love it. It's super cool. Just worth taking a look into. Don't let it overwhelm you because it gets real complicated real fast. But it's really neat stuff. So I hope that I answered your question satisfactorily, Ben, and I hope you guys learned a little bit more about the hardware side of things. If I think of any more really kind of substantive topics that I could put another one of these videos together on hardware, I will do so. Otherwise, from here, I think we're going to start shifting towards software, and then we still have the design process and that HMI tutorial that we're going to walk through, building one of those up from scratch so you can kind of see what those actually look like in practice. I mean, it's kind of sort of like a website or a kind of sort of like another piece of software you would run on your computer. It's just the design principles and what information you're putting on it and how and why and where is specific to industrial HMI and industrial SCADA. So we'll kind of show you the differences between what I do versus somebody who builds a website or somebody who builds desktop software for that you would use at home and or even at work in an office situation. We'll sort of compare and contrast some of those ideas, and there's some overlap in there too, but that's for a whole other topic set of videos, and we will see you next time, as we, like I said, move into the software side of things. Bye everybody.